I tend to break things into things that work with waveguides and things that don't. Waveguides, you got to get that light highly collimated in a little tiny hole. Something OLEDs don't do very well. I've seen an OLED into a waveguide. It puts out less than 1 nit. You have to be in a darkened room. You almost have to dark adapt your eyes to see the image. It's that dim.
Right.
Put an image out there. And that's because they put out what we call Lambertian light. Lambertian light is light that's kind of diffuse or spread out. Big problem with MicroLED, and we'll talk about that in a little bit as well. But basically, LCOS and DLP waveguide stuff. So behind all that is a WaveOptics waveguide, and it's old. It's probably 5 years old design in terms of the optics in there, and it's an old DLP design. You can see WaveOptics before they were bought was moving to LCOS. You could see that Dispelix, their older designs, were that they were moving to LCOS. And the reason they give is LCOS can get them to higher resolution, and B, it's a lot cheaper.
Yeah.
And there are multiple sources of it where you got to go to TI. Plus, TI has not been as price competitive. There are several companies still doing LCOS. RaonTech is out of Korea. They seem to be fairly aggressively doing it. They are hedging their bets. They're using their same silicon backplane to do a MicroLED prototype. Now, here's something important, though. When you look at MicroLED or any of these things, like LCOS, you have the backplane, which is CMOS. And it's pretty, compared to other things, compared to OLED or MicroLEDs, it's a fairly simple process. Plus, the backplane does not have to drive current. Remember, the light is coming from an external LED, so all the power is in the LED. There's not very much. It turns out that what you do is you just put a piece of glass and put liquid crystal in there. It has to be high precision assembly, so it's not easy. But LCOS is relatively simple to make. The silicon underneath is dead simple, really probably 5, 6, 7 generations old. CMOS technology, so it only doesn't have to support voltages or current. When you start to go here, a lot of people have started by taking LCOS. These were designs that weren't really designed to drive current, and they could build kind of dim micro-LEDs to proof of concept. But eventually, you have to build a more complicated structure because an LCOS is dead simple. You put a static voltage. There's no current to speak of. Just right as you change there's only current when you change the pixel value. So when you go to micro-LEDs, you generally have to have, instead of like 1 transistor, or in our case, we sometimes had 6 to build a static RAM bit. On these things, you now have to have a current drive structure. It's a bigger transistor. You have to have more power busing in the silicon, in the chip. So you have to go to a higher level technology. You need more metal layers. And you need smaller transistors, and you need more powerful transistors. So you tend to drive things up and cost a lot to go from LCOS, which tends to use grotty old CMOS, to doing MicroLED. And that's what we found with compound photonics, I think. Compound photonics was probably 2 or 3 generations more expensive and better technology. I never saw compound photonics get a product to market before they were bought. But they had like the most complicated silicon out there, which will also put them at a competitive disadvantage in doing LCOS. Maybe an advantage going forward in doing micro LEDs. I don't know.
I have a question about all this.
Sure.
We're also I'm starting to notice slightly, not very prevalent, but micro OLED companies are also kind of like looking into designing backplanes for micro LED. Is it much easier to transition the CMOS designs from OLED backplanes to micro LED backplanes?
Yeah, they're much more similar.
Yeah.
The big difference is that micro LEDs, to make them bright, have to have a lot of current. So that means you need a lot more power busing. But structurally, if you looked at them topologically, they're very similar.
Okay.
There's one company out there called Parotech, which is different altogether. Again, they just surfaced. Boy, just when you thought they'd bought all the big companies that bought all the companies that could in micro LED, a few more popped up. One who I had heard of but hadn't popped up. Google bought one of them.
Yeah.
And they weren't even, I think it was Raxium or something. They weren't on other people's radar screens. I knew of them because I knew one of the guys who went to work there. But They just put up, and then they get bought. All these other guys get bought, and next thing you know, you saw Vuzix bought somebody. I'll talk about that in a bit. But yeah, anyway, back to the backplane. Yeah, the backplanes are structurally similar, but you got to do a lot more currents. I think I talked about before, when you go from an OLED to a MicroLED, they're like 1,000 times brighter, but they're maybe 20 times more efficient.
Right.
Well, how do you get the difference between 20 and 1,000 is power.
Yeah.
There's a lot, and in this case, it's going to be current.
Mm-hmm.
So you got a lot more current going through there, and current's what melts wires. So I don't know how they're going to do it. And also, I think you'll see the micro, even in OLEDs. Like when you get like your OLED, your cell phones, how they dim. You'll see a lot of times they spec their brightness with 10% pixels on or something. Because if they put up a whole display of white, if you measure the light of a given pixel, it's going to be a lot dimmer.
Yeah.
They have to dim. Well, you got that problem in spades when you're talking things that can be as bright as MicroLEDs. I don't know what they're going to do if you put up a screen of white. I think it would melt.
Right.
So, I mean, but what they depend on is we saw way back with MicroOLED displays. A lot of this stuff is pretty sparse. Well, if you have a sparse display, you're not trying to read a web page, which could be anything, including all white. But if what you're trying to do is just put up arrows and directions and all, you might find that your average pixel value is less than 10%, maybe even 5%. Well, okay, now you're 5%. You just say you've got 1/20th the power. A lot of people have written off LCOS, and I have, as I said, I got into this. This is when I left Texas Instruments. I got into LCOS, so I know a bit more about this technology than the others because I literally designed some of these ICs. But what's happened is you had a bunch of guys like the MicroLED guys saying, "Hey, we're going to use this Jaybird display. It's 640 by 480, and it's going to be like a 15 or 20 degree field of view." And the LCOS guys, a few of them, particularly Digilens and Avegant, said, "Well, if all you want are 10 or 15 degree field of view and only want that many pixels, we can get a really tiny LCOS engine. It doesn't have to be this big." You guys they were off chasing the 50 and 70 degree field of view market.
Right.
If you want a little tiny field of view, we can build a really small engine too.
Mm-hmm.
And so we're seeing that. Lumus went from doing 1D waveguides to 2D waveguides. So this is in the waveguide front. And by going to 2D, they used to always be 1D, and that meant that they had to have a very large optics. 2D expand. What happened is with the older Lumus, they had to project an image that was effectively very oblong. They basically projected light that was like a big tall rectangle because it only expanded. They only did the pupil expansion in one direction. Their new stuff, their Maximus line, and I don't know if they're going to have other names for it, but the first product that was the Maximus. What they did is they expanded in two directions. They expand horizontally and vertically. And that let them make the engine a lot smaller because it didn't have to be a big and rectangular in one direction. And so they did that. Digilens is a little bit more what I'll call a conventional design right now. Avegant went fairly extreme. And then Magic Leap, the new Magic Leap 2 went very extreme. What they did was, is normally, and a conventional one, I took this slide straight from Magic Leap because they talked about what they did. But basically, normally you combine the red, green, and blue. You see this little X cube here? There's several ways to do this. One way is with an X cube. But this is the illumination path. And so the knock on LCOS has always been you have an illumination path, and then you have a beam splitter path that you've got to come in to hit the LCOS and then come out, and then the projection optics. Well, the argument for OLED and micro LED is that you're right here. You can you get rid of all this stuff, and now you're here and you've got rid of all that.
Right.
Well, what these guys figured out is, you know what, not so fast. There's some tricky ways we could do this. What they're doing is they're basically combining, they say in a waveguide, I've heard different stories. I haven't ripped one apart. but they're combining the LEDs in a line here, and then they're sending the light back through the projector optics. So what they're doing is they're kind of folding this all up, so it's a much tighter package. In the case of Magic Leap, and the funny thing is, I saw this, and then right after I saw this, I saw how Magic Leap was doing their stuff. And Magic Leap, what they did is they said, hey, you'll notice there's no beam splitter. Like this has probably got a beam splitter in it because the light's got to come in and, well, Magic Leap gets rid of the beam splitter because what they're going to do is they're using some trick, double circular, then you see circular polarizer. A circular polarizer is a linear polarizer with a quarter wave plate film. So we're back to our friends at ColorLink who are doing those quarter wave plate films. That's what a circular polarizer is. So anyway, they figured out that what they could do by doing this, they could put the LCOS panel between this polarizer using the magic of polarizers and switching with quarter wave plates, a lens. There's no beam splitter anymore. They're literally illuminating through the waveguide, come down, hit this thing, and come back, and then to the input ports of the red, green, and blue waveguide. So they've got no beam splitter. They've got basically they've got a little bit of projection optics, which they use twice, by the way. They're going to use this lens twice. They use it to illuminate, and they're using it to project. That's a little bit like these guys, because see what's happening here is they're literally sending this light through the projection lens. Right. So they're using the projection lens on the way in and back out. That's why I say this is like you can see yourself almost progressing from one to the other and do that. Now, Lumus is a bit more conventional. They use a thing called a light pipe integrator. These guys are doing some remarkable stuff, though. They're getting 3,000 to 4,000 nits per watt to the eye. To give you, for example, the Nreal is nearly a watt to get you 120 lumens. They're getting thousands, they're orders of magnitude more brightness for the same amount of watts in. So, and this is through a waveguide, which is relatively inefficient, although their waveguide, and I get different numbers, but somewhere between 3 and 7 times more efficient than the diffractive ones. But the beauty of LCOS is you can start with a really small light, and when you're trying to get this in this little tiny entrance pupil, the entrance area where the light goes in, that's all the difference. So anyway, so what's happened is LCOS is seeing somewhat a rebirth at the small end, and I call this the great bifurcation of the market. You have people who are doing, basically they're saying, if you want a glasses form factor and you want only 20 or 30 degree field of view, well, you can use LCOS. You don't need to go to micro-LEDs. We've got color solved already, all that stuff. So I think you're going to see a resurgence of these type of engines if that's what you want to do. I also heard I heard that Meta was also looking at a more informational display type glasses.
Yeah.
So we may see that. Now Lumus is trying to get all the worlds. They also have some even tinier engines that they're going for 20 to 30, but very bright. They're talking like 15,000 nits per watt to the eye. So they're talking massively bright, and they're looking at higher field of views to 70 and whatnot. So they're kind of in a different category here. But Digilens is got some really good lenses. They're doing a lot of innovation on the lens size. They're also working on that light coming out from the eye. But right now, their engines are much more conventional. And a lot of what they show is their older DLP. As I told you, my progression is Digilens I always thought was a reliable DLP house. They've been using DLP in their various designs for, golly, maybe a decade or more. And I see them doing LCOS engines. Avegant's doing a lot of different things. They're probably more famous in the community. They did some goggles that came down, some television, basically viewing displays that like a headset that rolled over. And they also were famous for doing some light fieldy light stuff. But I think they decided they're basically a technology company, and they figured out that, hey, if people are doing things like micro-LEDs and the laser beam scanning stuff on a small engine, hey, we can do that in a much more cost-effective manner. Here we go to Avegant. Here's their engine. Here's their 30-degree engine. Pretty tiny. They can do 50 degree for just a little bit bigger. bigger volume. It's actually a little shorter. It's back to how you do actually the lens on there is more wide angle, so it actually makes it shorter. But this is an actual working glasses. Now they're still being a bit optimistic. They're coming out with a cord just like Nreal and all. But this is a working set of glasses. Okay? And you can see that with the Dispelix. Now what the trick is they are front projecting still, but they're projecting down. And I'll talk maybe a little bit about that later. But what they wanted to do is emphasize, you may remember North Focals, they had a thing out with laser scanning. They had a 15-degree field of view. The image quality was terrible, and the eye box was almost non-existent. It was all you could do to see the image by moving it around and all. If you got those things, you had to have somebody fit them to your face and buy a custom everything. But you see, what they try to show you is here's their Avegant engine. They could literally fit their Avegant engine inside of the North Focal glasses. So this drives home the point that if all you want is a small field of view, there's a way to get there today, and not wait for all this stuff. As people may know, I'm not a big fan of laser scanning because every time, and like I say, I have no dog in the hunt, and for about 11 years, that's just the image quality. This is Digilens. This was actually taken at SPIE. This picture, they were at the show. So, but I once again, because I had done all this work with them in a prior show, I didn't spend a lot of time with them in the booth doing it. But what they did, this is, I believe, using a DLP. I thought at first it was LCOS, but it's DLP. But they do have an LCOS engine that they were showing working at the show. So they're, like I say, they're on the move, just like WaveOptics was before they were acquired. They were on the move to LCOS. And like I say, I don't think it's anything bad. I think there's characteristics of DLP people like.
Yeah.
It's just a matter of the market conditions, ability to make small, and the physics of making smaller pixels and cost. This is one I took. I put a 32x ND filters to take this picture because you see how bright it is outside. Yeah. And this is LCOS. They're doing up to 2,000 nits outside with LCOS. So they're getting there. I think they're probably using a bit more power than, and as you always have to look at field of view, this is like a 30-degree engine. The Lumus I was talking about before was a 50-degree engine. Well, that may not sound like as much, but that's a heck of a lot. That's like 3 times the field of view. You have to support that light over 3 times the field of view. Therefore, you got to take, so really 4,000 nits at 50 degrees is a lot brighter, a lot more light coming out than you would there. But anyway, so Digilens has got an LCOS engine. They were showing it at the show. I don't think they had it all up and working together. They had a separate demo and they had a separate thing showing it. But I think they need to work relative to Avegant. They're doing the whole deal, but I think they need to work on their engine. Avegant's being much more aggressive with the LCOS engine. One thing really neat with Digilens, though, and this is old picture. I went to their place at one point and got this picture. This was at SPIE, but they now got plastic working. They did have a better version of the booth, but I didn't have the setup in time to take a picture of it. So this is an old picture. It's a little blurry, but really important. They've got plastic working. That means it's going to be lighter weight, less fragile when you drop it. Plastic has a tendency to give, where glass has a tendency to shatter. That's by the way, an extremely important aspect of all this stuff.
Yeah.
This is something I see people working on. This slide, this lower one is from Digilens. It shows you they're focusing on it. They've got it down. This Maximus is currently at 5%. This is, when guys do prototypes, they tend not to do you spend a lot of time doing coatings. Coatings are expensive and they're also very time consuming. A lot of guys leave out the coatings. They say, okay, I know what that looks like. So like on Lumus Maximus, this was taken over a year ago, they didn't have all their coatings on. So I do want to emphasize that. Now, some of these guys may not be, they're all improving this and they all have ways to improve. But this is classic, what we see with all the headsets, the so-called front projection or glowing eyes effect.
Yeah. What
happens with diffractive waveguides, the very last diffraction is oftentimes 50-50, 50% to the eye and 50% forward. It may not look as bright because they may also have tinting up here, but this is where you get this glowing eye effect. This is actual, I if you're looking straight onto the guy and move all around in that cone, you do not see hardly anything coming out of the Avegant glasses. If you go down, if you go look at the bottom and look up, they've done some things to cut the amount of light, but they've also done some things to project it downward. And both these companies, and I think I've got a slide showing that in a sec, I do. So they do that. Lumus inherently is less, if you look at the way it's structured and all, tends not to project forward. They're tending to send all the light either to the eye or into the side of the glasses, basically, that gets absorbed. But you'll see this with most diffractive waveguides, including Snap and Vuzix, Microsoft, and whatnot. So they're doing a lot. And then, of course, Digilens emphasizing here how they are working to reduce that. Matter of fact, Dispelix is doing a similar thing. It turns out this is kind of a good thing in a way. Most people want to cant the glasses, tilt it, so that the light is so that the glasses actually tilt in, and that's what your normal glasses oftentimes do. Well, what they can do is, it turns out that there's a doubling effect. If you tilt it down a little bit and design the thing accordingly, you can then make the light it doubles that angle. So by whatever amount you tilt by, it shoots the light down at twice that angle. So you basically are shooting at the floor rather than shooting into the eyes of the person next to you. Funny enough, Digilens knows the same physics. They get to play with the same physics. And they can do this either from the side. You can make it if you tilt the glass. The other thing people tend to do is wrap glasses around the eye. If you do that, you can have the light eye glow shoot out in a different direction, or you could tilt it the other way like Dispelix was doing and make the light hit the ground. So there are ways to kind of ways, and it looks natural because a lot of times glasses are tilted and whatnot anyway, either horizontally, vertically. So that's what those guys are doing. I wanted to bring these guys up. This is kind of neat, and I don't know whether this makes a lot of sense or not, but I found it interesting. You know, people, the holy grail for LCOS would be to be illuminated by lasers. Now, you still got the interference issue we talked about earlier with laser beam scanning, but in some ways you get all the benefits of LCOS. You get this kind of focus-free nature. You get really highly efficiency relative to the light source if you can illuminate with lasers. What these guys have, this is a VitreaLabs or somebody, they're in Europe someplace. They've got a thing where they basically have this structure that takes that laser light and has a waveguide that's going to do it. And there's little teeny tiny mirrors, effectively. They're going to shoot this light up. So they're literally taking a single laser beam and keeping it as a laser. They're not just a diffuser. It's literally, they're going to take the laser beam, and you kind of see it starting here. They're going to split that laser beam and make it into a whole an array of little tiny lasers. Now they can do this for an LCD where they end up with a laser per pixel. So imagine each pixel in an LCD is individually illuminated by a laser. So now you've got super highly collimated light. You've got basically laser light. The other way to go is to use this to illuminate an LCOS device. Now, whether this will pan out, there are definitely problems with speckle.
Yeah.
These things showed a lot of speckle. I don't know if they can solve all that. It's just scientifically interesting.
Right.
So I'm not. It's one of those things I would look, if I was a company working in this field, I would look at it.
Mm-hmm.
I'm not saying it will work. I have not vetted it for the physics working.
Right.
But it at least has. And this is that grass is greener problem. It's like, why did HoloLens 2 use lasers? I think they looked and said, well, we have this problem with LCOS. We won't have this problem. What they didn't realize is they bought a bunch of worse problems when they moved to laser beam scanning.
Right.
Laser beam scanning. What they do with laser beam scanning, it sounds simple, and they always try to make it out to be that what you're doing is you take a set of 3 lasers, usually if you want color, and they have a mirror, sometimes one mirror, oftentimes 2 mirrors, that scan it in X and Y, and they scan the laser back and forth really fast to try to generate an image. You've got to do it at least 60 times a second, which is really not enough, although many, that's all they do, which will then cause flicker. Usually one mirror is scanning really fast, and there's another mirror going more slowly that then can reset back up. So one mirror is kind of just oscillating, and it's a complicated process, changing velocity constantly. So it's really complicated to control the laser with the same brightness, because because it's speeding up and slowing down all the time. That means the brightness is constantly inherently changing. So you have to then modulate the light just to try to create that uniformity. That the laser is always scanning nonlinearly. It's not scanning in a rectangle. So what happens is scan lines do not equal pixels. As we talked about earlier, you can try to fix if you have a normal image that's on a rectangular grid, you basically have to reprocess it and rescale that image onto the grid of the laser beam scanning. Generally, lower resolution uses a single mirror that scans both ways. And then the higher resolution, to get the higher resolution, they have one mirror that just does horizontal. And that mirror is really tiny because it's got to wiggle really fast. And a second mirror is a bit bigger because that image has been scanned a bit. There's another mirror that's a bit bigger, usually kind of oblong, because the image has been kind of stretched by one mirror. That mirror is moving slower, and that's typically vertical scan mirror. The whole thing doesn't work very well. They can't really move. The fundamental problem is they can't move the mirrors fast enough. Not to mention all the distortion they create. I've never seen a laser beam scanning system that was within half horizontally and vertically of the resolution that was claimed. They always talk some theoretical resolution, but when you actually were to put up a test pattern and measure it, it's always a quarter of the pixels that they claim to have. And that goes from Hololens. The most famous thing out there using laser beam scanning is the Hololens 2, and we'll dig into that some more in a bit. Here I'm talking about mostly companies related to the laser. There's a thing called the LaSAR Alliance, which is a bunch of laser beam scanning companies. ST Micro is one of the big makers of the mirrors. That's how they got involved in this, to speak of. ST Micro makes all kinds of electronics, but they're most famous and unique for their building of little micro machines and micro things. They're and all kinds of motion sensors, transducers, all kinds of things that involve something that moves. Well, oftentimes they're the company that designed it. The guy who actually makes the product is somebody else. In the case of Microvision, their mirrors were being made by ST Micro. So when HoloLens 2 got built, as far as I understand, they just got the design from Microvision. They went directly to ST Micro to build it. So anyway, so ST Micro is a maker of it. Then they formed this thing called the Laser Beam Scanning Alliance, or LaSAR. And unfortunately, it's kind of I've been in the industry 44 years. I've seen a lot of these things. It's kind of a conglomeration of companies with similar interests. So Dispelix is in it. ST Micro is the big head. I believe Applied Materials, which is a very big guy for making waveguide, the waveguide blanks and waveguide processing. You have companies involved, but they're involved in different ways. Some are really involved and really dependent on it. But ST Micro is kind of the hub. It seems like they're the ones that push it. They're the ones that put on this big booth where they talk about it. There's a company called Augmented that's in it. But they each have different interests. I think Dispelix is kind of like, oh yeah, we work with everybody. We might as well go in. There's a lot of free publicity. The problem you have is it's a combination of guys who make stuff. What they're missing is the guy who makes the end product, the guy who makes the headset.
Yeah.
And it's kind of like they wouldn't necessarily need this alliance if there was somebody making the headsets with it. And I think the problem is when you drive up and see the stuff, I mean, laser beam scanning always makes all these claims. And one of the reasons why I'm so down on the technology or have so many problems with it is it never matches up to what they claim. It's always higher power. It's always lower resolution. It's always got poor image quality. One thing HoloLens found out, they spent hundreds of millions of dollars to try to do this stuff. And they ended up with a really horrible looking display. And we'll talk about a little bit of that later. And I've got all kinds of stuff on my blog that talks about that. But anyway, ST Micro is kind of the hub of the Laser Alliance. First of all, there's a company out there, Augmented, and what they were doing is a Lissajous pattern scanning. They had a single mirror that's wiggling all over the place. It's both, you know how I talk normally, they have like two mirrors and one going horizontal, one going vertical. They have a single mirror that's just free running, making a Lissajous pattern, which is basically a two-dimensional sine wave. So it's eventually it should hit all the pixels. But like here, I took a high resolution, high-speed picture at 1/500. The problem is this checkerboarding thing, or it's basically randomly hitting the pixels, but you got to realize what your eye does is integrate light over time. So in some places, like where the beam crosses, it's going to be brighter than the gaps where it misses.
Yeah.
And so you keep doing this again and again, and you still get bright hot spots and dark spots. It's kind of like random walk to try to hit the pixels, but you're not hitting all the pixels at the same amount. So then you have this thing, how would you ever compensate for that? How would you make the image look uniform? I don't think it ever gets there. I think it's the wrong technology. By the way, this technology, though, might be really good for doing things like LiDAR. Because with LiDAR, you kind of like this idea of not going in a nice fixed order. If you were trying to detect objects, you kind of like the idea it jumps all over the dang place. That's actually a good characteristic in LiDAR. It's a lousy characteristic in display. I think it's the exact wrong technology for making a display. And I told him that. But then you have other guys doing, like I say, this is in their booth. I think this is with ST Micro has a demonstration thing. If you kind of look at this thing, you say, that's a pretty dang low resolution image. You kind of look at these things, you say, these are pretty low resolution images and not very good quality.
Yeah.
This is Augmented in the Dispelix. So this is a Dispelix waveguide. I don't think they're controlling the colors very well because you have other problems that compound themselves. As I told you with Hololens, I think they thought, oh, we have these issues with LCOS. We'll just go to lasers and that'll solve all these problems. Now they just got a bag of new problems. And one of which is apparently it's much more critical in how you align and do things with lasers, with waveguides, that you create problems. You also have interference problems that are created. So you just kind of traded problems. And so anyway, but once again, we're talking very low resolution images. This also is showing that Augmented, you can kind of see the grid that's in there. And remember, you're trying to translate now this rectangular image, with square pixels effectively, onto this really weird ass grid, and say turn the laser on and off on this thing. It's a hard problem. So you just munch the problem around, and I think you create a problem that is pretty much insoluble. The worst problem I have, though, when you net it all out, if you do I have a thing on my blog, I've done this before. If you do the 4th grade math, when I first heard HoloLens 2 was using lasers, the first thing I heard is they were using 50 kilohertz for the horizontal mirror. 50 kilohertz may sound fast, but you got to realize old-fashioned television was interlaced, which is really only 30 hertz refresh, or half the number of lines at 30 hertz.
Right.
With 15 kilohertz. That's 15 kilohertz was in some digits, but around 15 kilohertz was the horizontal scan frequency. Turns out if you take 50 kilohertz, you don't get anything like, if you take 50 kilohertz for the horizontal scan rate, and knowing how crapped up the scan process was, yeah, I knew the resolution couldn't be there. And all you had to do is tell me that one number. And 4th grade, if that number, and knowing how the thing worked, and some 4th grade math, you can know it doesn't support the resolution that they claimed.
Yeah.
So that's always the problem with laser scanning. It always disappoints every time. I have a saying that, and we'll see if HoloLens breaks it. You can kind of say the military is almost a second product, but historically, with Microvision and their laser scanning, it's been one and done. There's been about a dozen or so different products. They never did Gen 2. It's always one and done. They get there and they barely, if they get to market at all, they barely get it over the finish line. People look at it and say, "God, that's not very good." An interesting company also out there in the laser scanning thing is Luminit. They're doing the holographic waveguide. One of the problems that people talk about doing direct scan where they kiss off the mirror. Remember that thing I was talking about back with twos and all, that you've got to direct the light to the eye. If I put a mirror coating on the front of these glasses, the light would shoot out, hit there, and hit your nose. It wouldn't hit the eye.
Yeah.
So what you do is you can actually build into a hologram power that makes it look like it's a tilted mirror. It's kind of magical. It only works with lasers. You have to have very narrow amounts of light, but you can then kick the light back towards the eye. It still has some of the problems that it spreads out, and if you do color, try to do this with color, you have to have like 3 layers of holograms or build it in the hologram, and you get effects that look a little bit like what you see with a diffractive waveguide. There's a very thin line between what's a hologram and a waveguide, and we won't get into that, but you do get the problem that you don't get this nice, pure, simple image when you do this stuff. But anyway, I brought up Luminit because Luminit's used with the laser scanning. They also have some things where they do a holographic lens. This is actually, if you look how big this image is, this is farther away, but you notice how it's bigger?
Yeah.
They've literally built this as a mirror. It looks like your bird bath mirror. It looks like a curved mirror. And they build that into the hologram. They built optical power. As you can kind of see here, it's a prototype, and what they said was the wavelength. This, by the way, is an LCOS laser engine. It's an old-fashioned LCOS one. I think this probably even used my chip in it. But this looks, I believe, is an LCOS laser engine. It's not laser beam scanning. It's going on to a diffuser here that they're magnifying to build effectively a rear projection. So this is magnified. They also can build diffuser film. This has got no optical magnification, and it's just basically taking a projector light and making it kick back towards your eye. This one's, to me, more interesting, where you basically build a flat lens. You can basically build any kind of lens into that. And it's kind of interesting now. Whether it becomes practical or not, I don't know. I can tell you the problem with this one, when you do direct laser scanning, that's what everyone thinks about, by the way, when they think laser beam scanning and glasses. This is a total failure, and the reason why is, if you think about that laser beam, we've talked a little about eye boxes and a little about pupil expansion, like waveguides do pupil expansion. Well, why they do that is if I take that laser, kiss it off, that laser beam is either going to hit your pupil, in which case it's very bright, or it's going to miss your pupil altogether. So if your eye is jittering around and moving around and your glasses are moving around, it's kind of hard to hit the eyeball. That's why if you looked at North Focals, they had to build you custom prescription. They had to custom align the whole damn thing to get it to hit your eye, because they had a 4-way pupil expansion. But what that meant is, depending upon where the things lined up, you either saw double or quadruple images, or no image at all if you're a little bit off. But that's this idea of needing pupil expansion eye box. That's a lot of what the waveguide's doing, is replicating the pupil. It's actually making it so no matter where you look, you see the image. And that's North Focals didn't have that. So this is the problem with direct scan into the eye, is the eye box is infinitesimally small. Now, there was a company called Eyeway. They went out of business, but they were working on this foveated thing. And what they were going to do was track your eyeball and move the laser beam to track your eye. You then get back to the same, everything's connected. It's a connected world. You go back to Mojo Vision. You now got the problem is, when the eye jitters around, will your brain interpret that as a stationary image or an image that's moving around?
Yeah.
It's a hard problem. And I think it's one, I mean, back when Eyeway was still, they went bankrupt very quickly. There was some interest. There was rumors they were going to get bought. And there was a big company that, from what I've heard, was all ready to buy them, but the deal fell apart at the end. And I think it makes a lot of sense maybe to a big company, because they were doing some really interesting eye tracking stuff. But I don't think they'd solved it yet. They had never, their next stage was to demonstrate they'd solved it. If somebody can solve that problem, they got something, because I think it's a really interesting problem to solve. Even if you solve that problem, it still may be 10 or 20 years before it's in glasses that you can buy in the store. So anyway, wanted to mention this company. They were TruLife. They're out of England, out of London area. They have a curved holographic waveguide. They do both. They did very similar to these guys. It's like guys who do hologram do this stuff. They have the kiss off the eye thing, so they have that too. They do a waveguide for that, and they do holographic things. They can do them on a curve now, they say. So that if you're doing the thing of encasing, they're working with that same company, Luxexcel, that's encasing waveguides in plastic. So they claim they can build a curved waveguide. Now, their only demonstration right now, this demonstration had a fixed slide, so they had it's a very crude presentation of it, but they were doing a curved waveguide, so using holographic films. Once again, and they've also done those things like building mirrors. I've been to their place years ago, and they were doing stuff like this too, where they build a holographic mirror. There's things you can do with holograms. Problem with the holograms is usually the image quality is not as good as you get with traditional optics. And mirrors are like, the reason why everyone tries to use mirrors when they can is mirrors are like that they don't have the breakup of light problem. You don't see this thing where you see the colors breaking up. Prescription lenses. One of the big problems we have is if these are going to be glasses, and this is still high-end stuff, but we talked before about TUS. TUS was doing injection molded prescription lenses. The company making all the rounds. I mean, they literally have, I think they claim they have like 20 companies, and I can believe it. Everybody and his brother seemed to say they were doing something with it. Lumus is working with them. WaveOptics was working with them, which probably means Snap is going to look at it. So everybody's looking at how do you get prescription lens built into the waveguide, so you don't have to build something. The worst case scenario is you build put plastic on either side of your waveguide, and then have to add lenses on top of that. So everybody's looking at that. The problem with this is that, it's great for prototyping. It's really good to get lots of guys using it because, hey, I don't have to, like in the case of TUS we talked about, they have to build a mold. Molds are tens of thousands of dollars. They got to build mold, really high pressure and very high precise molds for the optics. Whereas here, they're literally 3D printing the plastic. So they're doing a thing. The problem here is that the per unit cost doesn't come down very much. I mean, it'll come down with volume, but it never gets to be as cheap as something you inject and mold, and you maybe spend $1 or $2 on the injection molding.
Right.
This is always going to be expensive because it's always going to take a long time to do it. From what I can understand, Luxexcel is primarily in the ink business. They want to set up third parties to actually do all the printing. They're not the company. They'll do the printing for a company, but they're not going to for an initial start. The thing that makes them really attractive, though, they're really easy to prototype. It's a little like FPGAs. You hear about people doing things in FPGAs.
Yeah.
The custom IC, certainly a lot less work. Company that was at the show is Meta. And to be emphasis here, big bold letters, not Meta. This is Meta that existed when there was the Meta, the optics company, but this is Meta Materials, not to be confused, and not a part or any association with Facebook. Meta Materials had several interesting things in their booth, but one of their things, and they bought a company. They acquired the IP from a company called Interglass that was founded in 2003. So this is not exactly new news, but Interglass has a process where they use. Remember how I told you how, like, if you're, it can cost you tens of thousands of dollars to make a mold for plastic.
Yeah.
But what these guys do is they're using glass molds. And what you can do is you can take the glass, and they have a video that shows how this works. But if you take the glass, you can basically build glass molds really cheap. So what they do is their molds are made out of ground glass. So you make a precision mold out of glass. And it turns out for astigmatism and other things, you can kind of twist these things around and get a lot of the in-between values out of a fewer sets of molds. And then what they do is they do a UV curable plastic that they squeeze. You can kind of see it filling right here. They squeeze between these two glass molds to make the lens. Well, what you can do is, if you can do that, you can embed stuff in it. Like they showed embedding like cameras and sensors and things. So you can start embedding stuff, and then they UV cure this thing. Now the plastic they use is not as durable plastic as this is usually an acrylic type plastic, whereas TUS I think can do polycarbonate, which is a little more durable. I find it interesting that because all the talk, Luxexcel is all the talk, they're trying to get back in the conversation, even though they're actually using something that came from a long time ago.
Mm-hmm.
And so they're showing here embedding different things, like embedding your LEDs and cameras and stuff like that. My father and two brothers were patent lawyers. I'm sure the patent people and the trademark people at Facebook told Zuckerberg, this is a really stupid name. Everybody, his brother has this name. The considered most ideal name in the history of trademarks is Kodak. It was a totally made up word. Kodak, George Eastman came up with Kodak for his company. And the beauty was that he owned that name. And he got to be so synonymous with photography that people talked about taking a Kodak or using a Kodak, which would be a camera. And he was only able to keep his name due to the fact that there was that he had such a strange name for it, and they would enforce it. They had to enforce it as a principle of trademarks.
Yeah.
You have to enforce your own. You have to go around suing people. That's why some of the things Disney does are just to be evil, maybe. But a lot of it's because they got to protect their trademark. If they don't do that, if they don't stop people from using it, then you can become like Kleenex. Kleenex almost lost their name for facial tissue. Kleenex, another famous one. But anyway, Kodak held their name, and part of it was because it was so unique and easy to protect. Meta's got like nothing. I mean, and Meta, they spent a lot of money on that name, and I think they'll continue to spend money on that name to protect it. Now, if you're Zuckerberg and you have a huge ego and a big wallet, yeah, you can do it. But it's I didn't consider it a very, it wasn't a nice move. It basically set people up against you. It makes you look evil. And there are already lots of companies out there with the Meta name, including the company they bought it off of, but there's actually several other people in this field. Not to mention the fact that I think the origins of it are pretty evil. I think it comes from a book.
Yeah.
And it's a pretty dystopian future. So on top of all that, but Zuckerberg wanted the name, so he got it.